Hi, welcome to this video from a question from the Romanian Mathematical Olympiad. Now, they want us to prove that this tricky looking binomial is always divisible by 2 to the n minus 1, where a is defined as so. Now, this is quite tricky and I recommend trying it yourself. It's quite a fun problem. There's lots of different ways to do this. We're going to be specifically using a way that exploits the Chebyshev Polynomial relation, which I'll talk about what that is later if you don't know. So first of all, let's have a look at this question, get some ideas on how to convert it. So first of all, we realise that the binomial coefficients increase in 2's, but the negative and the power of a increases in 1, or has a period of 1. It goes negative plus, and the power sort of only increased by 1 each time, which is quite tricky. So it makes us think that we're going to have to consider square root of a. And because our whole idea here is going to try convert this into sort of, I don't know, a c plus b to the n, maybe subtracting a c1 plus b1 to the n. Basically, we want to try simplify this binomial into a much nicer binomial. So if you play around with this, you can actually find quite a nice one, which is 1 plus I root a to the n. And this one gets kind of close. We get n choose 0 plus I n choose 1 a to the half minus n choose 2 a, which matches up with this, plus, well, actually no, still minus I n choose 3 a to the 3 over 2, and finally we get plus n choose 4 a squared, and the terms actually continue on like this. Now this is pretty close, but we've got these terms that we don't want. But do you notice something in common with these? The I. So we can do a little trick with this. We can take the real part on both sides. So we get 1 is the same as the real part, or 1 plus I root a to the n. Now generally any real part question, you're going to want to convert it to modulus argument form. So let's go ahead and do that. Let's say z equals 1 plus I root a, and theta is the argument of z. Then this is the same as modulus of z to the n cos n theta, where we've used the Mars theorem to bring the n inside. Now at this point it looks kind of like an induction. Why does it look like that? Well, we can easily split the modulus of z up like so, and this is probably not going to be the way we want to split it up, and likewise we can also split up the cos n theta using our sort of double angle rules. Now actually you can do a bit more of a specific way on that, but first let's see if we can prove the base case, because if we can't prove the base case it's going to be pretty tricky to do this. So remember what we're trying to do. We're trying to prove that this is divisible by this. So let's consider first of all n equals 1. Now if n equals 1, we're doing the real part of 1 plus I root a, which is equal to 1, and well, clearly 2 to the 0 divides this, because 2 to the 0 is just 1. Okay, then let's do n equals 2. So we're doing the real part of 1 plus I root a squared. Well, this is going to be the same as the real part of 1 plus 2I root a, which is imaginary, so we'll discard that later, minus root a. Well, minus a now. Root a times root a. And that's equal to 1 minus a. But remember, a was defined in terms of k up here. So we have 1 minus 4k plus 1, which is equal to 2 minus 4k. And clearly 2 to the 1 divides 2 minus 4k. Nice, okay. So we've proved it for our base case, which means we can assume it's true for n and n minus 1. And here's where we need to use a clever trick. This here looks a bit like the Chebyshev polynomial. Tn cos theta. Now, why is this a polynomial, you might ask? Well, if you say x equals cos theta, in fact, when you split this up, you'll get a polynomial in x. This polynomial has then lots of applications in numerical analysis. Now, the nice thing about Chebyshev polynomials is they follow a recurrence relation. Tn plus 1 of x is equal to 2x Tn of x minus Tn minus 1 of x. And this relation is what we're going to exploit here. So if we're assuming it's true for n and n minus 1, we can involve the nth term and the n minus 1th term. So let's consider the real part of 1 plus I root a to the n. We know this is the same as absolute value of z to the n plus 1 of cos of n plus 1 of theta. And well, by our Chebyshev recurrence relation, this is the same as absolute value of z to the n plus 1 times 2 cos theta. Replaced x with cos theta. Tn of cos theta is cos n theta minus cos of n minus 1 theta. Now you might be thinking, well, this is just a trig identity, but it's not really a standard trig identity, and actually to derive this identity, you have to do a little bit, you have to do some tricks. You do a double angle formula on this. It will split, and we almost immediately get this, except we'll have just one of them. We're not going to get this, we're going to have like a sine part, but then we can use product of sum rules, sine A times sine B rule. And what that'll do is that'll create this term again, but half of it, and you can bring that over, and then everything's going to follow from there. So it's not an immediate trig rule that we can just come up with. It's definitely something, if you know the relation, this part becomes a lot easier. Okay, now at this point we can distribute the absolute values of z's quite nicely. So we can bring out 2 from this part. We're going to have modulus of z cos theta, which we know is divisible in the n equals 1 case, multiplied by modulus of z cos n theta. This one's now going to be to the power of n. And then we're going to have minus modulus of z squared times modulus of z to the n minus 1 cos n minus 1 theta. Here we can use our induction parts. So, well, clearly 2 divides it. Here, well, this is where n equals 1, so 1 divides it, which doesn't really tell us anything, unfortunately. Here, well, we're told that 2tn minus 1 divides it. And, well, here we've got that 2tn minus 2 divides it. So clearly, 2tn divides this part. But this part, we've only got 2tn minus 2, which means we need 2 squared to divide it. I'll put a little question mark because we want to prove that. So to finish off our proof then, we just need to consider the modulus of z squared. But that's equal to the z times z conjugate, which is equal to 1 plus I root a times 1 minus I root a. And well, that's 1 plus a, which is equal to 4k, by using its definition at the top here. So clearly, that's true. So our induction works. We've shown if it's true for n and n minus 1, it is also true for n plus 1. We've shown it for our two base case, n equals 1 and n equals 2. And so we're finished. We've proven that for all k in z's, this is going to be divisible by 2 to n minus 1 for all n as well. I think it's a really nice proof. I hope you enjoyed. There's another way you can prove this. You can create a different type of recurrence relation. I recommend having a go at trying to do that. Thanks for watching.